Okay. Hi everyone. So today we are going to discuss about hydrogen peroxide concept. So actually hydrogen peroxide formula H2O2. Hydrogen peroxide formula H2O2. So first of all, preparation methods. Preparation methods, that is laboratory methods. Laboratory methods like sodium peroxide Na2O2 plus H2SO4. H2SO4, barium peroxide BaO2 plus H2SO4, and Metz process BaO2 plus H2O plus CO2. So these are laboratory methods. And next one is industrial methods. Industrial methods. So that is electrolytic method and auto oxidation. So these methods are completed in previous class. Next, properties of hydrogen peroxide. Oxidizing properties and reducing properties. Oxidizing properties, for example, lead sulfide plus hydrogen peroxide, potassium iodide plus H2SO4 plus hydrogen peroxide, formaldehyde plus hydrogen peroxide, benzene plus hydrogen peroxide in the presence of ferrous sulfide. Next, ferrous sulfide, estified ferrous sulfide, FeSO4 H2SO4 plus hydrogen peroxide, and potassium ferrocyanide converted into potassium ferricyanide. So these oxidizing properties are completed in previous class. So preparation methods and properties of hydrogen peroxide and oxidizing properties of hydrogen peroxide. So oxidizing properties of hydrogen peroxide like PPS, formaldehyde, potassium iodide, ferrous sulfide, next benzene, next potassium ferrocyanide. So these topics are completed in previous class. And next heading. Actually heading properties of hydrogen peroxide. Properties of hydrogen peroxide. Properties of hydrogen peroxide. And Roman number 1, oxidizing properties. So already completed in previous class. And Roman number 2, very important, reducing properties. Reducing properties of hydrogen peroxide, formula H2O2. So Roman number 1, oxidizing properties of hydrogen peroxide. So oxidizing properties are already completed in previous class. And next one, reducing properties of hydrogen peroxide. So generally reduction means addition of hydrogen atoms or removal of oxygen atoms or decreasing of oxidation state. So heading, reducing properties of hydrogen peroxide. So first reducing property, that is reaction with chlorine formula Cl2. So first of all, hydrogen peroxide or compound hydrogen peroxide formula H2O2 plus chlorine molecule formula Cl2. So very simple answer, 2 moles of hydrogen next to 2 moles of chlorine. So 2 moles of HCl, hydrochloric acid, and byproduct is oxygen gas. So removal of oxygen atoms. So it is one of the reducing property. And second one, react with bromine molecule formula Br2. Hydrogen peroxide formula H2O2 plus bromine molecule formula Br2. H2O2 plus Br2. So very simple answer. So 2 moles of hydrogen next to 2 moles of bromine. So 2 moles of HBr, hydrogen bromide, and byproduct is same, that is oxygen gas. So reducing property, chlorine or bromine, both are same. So H2O2 plus Cl2. So 2 moles of hydrochloric acid plus O2. Same H2O2 plus Br2, 2 moles of HBr plus O2. And next one, react with silver oxide or disilver oxide formula Ag2O, disilver oxide. So first of all, Ag2O plus our compound hydrogen peroxide formula H2O2. So very simple answer, 2 moles of silver. So 2 moles of silver Ag plus water molecule H2O plus oxygen gas O2. So very simple, 2 moles of silver, next H2O water, next O2. So first one chlorine, second one bromine, third one disilver oxide formula Ag2O plus our compound H2O2. So 2 moles of silver, H2O water molecule plus oxygen gas. So first reducing property, react with chlorine, second reducing property bromine, and third one is disilver oxide formula Ag2O. And next one, fourth one, Fourth reducing property is reaction with ozone. Reaction with ozone. Generally, ozone formula O3. Ozone formula O3. First of all, our compound hydrogen peroxide formula H2O2. Hydrogen peroxide formula H2O2 plus ozone formula O3. Ozone formula O3. So chlorine 2 moles of HCl, bromine 2 moles of HBr, Ag2O Ag. Next same reaction with ozone. H2O2 hydrogen peroxide react with ozone. Ozone formula O3. So very simple answer. Then hydrogen peroxide converted into water. Water molecule formula H2O plus 2 moles of O2. Oxygen gas 2 moles of O2. So for example, 2 hydrogen atoms, 2 hydrogen atoms. Next to 2 plus 3, 5 oxygen atoms. 2 into 2, 4 plus 1, 5 oxygen atoms. So reaction with ozone. Very simple. Hydrogen peroxide formula H2O2 plus ozone formula O3. Then H2O2 converted into H2O plus O2. H2O plus O2. And next most important reaction with sodium hypochlorite. Sodium hypochlorite. Reaction with sodium hypochlorite. Reaction with sodium hypochlorite. Sodium hypochlorite. So generally sodium hypochlorite formula NaOCl. NaOCl. Sodium hypochlorite formula NaOCl. So generally sodium hypochlorite formula NaOCl, but sodium chlorate formula NaClO3. NaClO3. So first one is sodium hypochlorite and second one is sodium chlorate. Sodium chlorate. Okay. So this is sodium hypochlorite and formula is NaOCl. NaOCl. So first of all, sodium hypochlorite formula NaOCl. So this is sodium hypochlorite. Sodium hypochlorite and formula NaOCl plus our compound hydrogen peroxide formula H2O2. Hydrogen peroxide formula H2O2. So very simple answer NaCl. So main product is sodium chloride. Formula NaCl. And byproduct is very simple H2O. Water molecule H2O plus oxygen gas. So very simple NaOCl plus H2O hydrogen peroxide. So main product is NaCl plus H2O water molecule plus oxygen gas. So first one ozone formula O3. Hydrogen peroxide H2O2 plus ozone H2O plus O2. Next to sodium hypochlorite formula NaOCl. Okay, NaOCl plus our compound hydrogen peroxide NaCl H2O plus O2. Okay, so first one chlorine, second one is bromine, and third one is ozone. Next to sodium hypochlorite, disilver oxide formula Ag2O. And next to sixth one, react with lead dioxide. Sixth property, react with lead dioxide. Generally lead dioxide formula PbO2. Lead dioxide formula PbO2. Lead dioxide. Okay, first of all lead dioxide PbO2. So compound name is lead dioxide formula PbO2 plus our compound hydrogen peroxide formula H2O2. Hydrogen peroxide. Very simple. Then lead dioxide directly converted into lead monoxide, that is lead oxide PbO. Lead monoxide PbO. So lead dioxide formula PbO2 and lead dioxide converted into lead monoxide formula PbO or lead oxide, and byproducts are very simple H2 and remain one oxygen atom, water H2O plus oxygen gas. So lead dioxide directly converted to lead oxide formula PbO. So lead dioxide formula PbO2 plus hydrogen peroxide formula H2O2. Then lead dioxide converted to lead oxide PbO H2O remaining one oxygen atom. So H2O plus oxygen gas. And important property, reaction with acidified potassium permanganate formula KMnO4. Very important reaction. React with acidified, that means presence of acid. Acidified potassium, potassium permanganate, formula KMnO4. First of all, KMnO4, potassium permanganate, KMnO4 plus acidified, that means presence of acid, formula H2SO4 plus our compound hydrogen peroxide, formula H2O2, three reactions. So first of all, potassium permanganate formula KMnO4 and acidified potassium permanganate, that means sulfuric acid plus hydrogen peroxide, formula H2O2, three reactants, potassium permanganate, sulfuric acid and hydrogen peroxide. Then potassium permanganate directly converted to potassium sulfate. So formula K2SO4, potassium sulfate plus manganese sulfate, MnSO4. So MnSO4, manganese sulfate plus water molecule formula H2O plus oxygen gas formula O2. So this is reaction. So potassium permanganate formula KMnO4 plus sulfuric acid formula H2SO4 plus hydrogen peroxide formula H2O2. So potassium sulfate K2SO4, manganese sulfate MnSO4, water molecule formula H2O, and byproduct is oxygen gas. So very simple. For example, 2 moles of potassium. Okay, 2 moles of potassium. 2 moles of manganese, 2 moles of manganese, Mn plus 2. And next one, H2SO4, 3 moles of H2SO4 and 5 moles of hydrogen peroxide. Next one, hydrogens, 5 into 2, 10, 3 into 2, 6, 16 hydrogen atoms, so 8 into 2, 16. Next to oxygen atoms, very simple, 2 into 4, 8, 3 into 4, 12, 12 plus 8, 20, 20 plus 10, 30. So continuous one, for example, 4, 2 into 4, 8, 8 plus 4, 12, 12 plus 8, 20, and 5 into 2, 10 oxygen atoms, 30 oxygen atoms. Okay? So 2 moles of potassium, 2 moles of potassium, 2 moles of manganese, 2 moles of manganese. Next 3 into 2, 6, 5 into 2, 10. So 16 hydrogen atoms, 8 into 2, 16 hydrogen atoms. Oxygen atoms 2 into 4, 8. 8 into 3 into 4, 12, 12 plus 8, 20 plus 10, 30. So 4 plus 8, 12, 12 plus 8, 20, 20 plus 10, 30. So this is reducing properties of hydrogen peroxide. So lead dioxide formula TbO2 plus H2O2, TbO plus H2O plus O2. Potassium permanganate formula KMnO4. 2 moles of potassium permanganate are acidified potassium permanganate, sulfuric acid plus hydrogen peroxide formula H2O2, then K2SO4, MnSO4, water and oxygen. And last and final reducing property, very important property, that is important property, reaction with potassium ferricyanide, potassium ferricyanide, not ferrocyanide, potassium ferricyanide. Generally potassium ferrocyanide formula K4FeCN6, but potassium ferricyanide formula K3FeCN6, K3FeCN taken 6. So this is potassium ferricyanide. Ferro, low oxidation state. Ferri, high oxidation state. For example, in potassium ferrocyanide, iron oxidation state is +2. But in potassium ferricyanide, iron oxidation state is +3. Low oxidation state ferro, high oxidation state ferri. So reaction with potassium ferricyanide, ferricyanide. First of all, potassium ferricyanide. So potassium ferricyanide formula K3FeCN6. K3FeCN6 and compound name is potassium. Ferricyanide. Not ferro, ferricyanide. Formula K3FeCN6. But in the presence of basic medium or alkaline medium, alkaline means basic. So base, one of the base, that is potassium hydroxide, formula KOH, potassium hydroxide. So potassium ferricyanide react with base, one of the base, that is potassium hydroxide, presence of alkaline medium, potassium hydroxide. Place our compound hydrogen peroxide, formula H2O2, three reactants. So potassium ferricyanide and alkaline medium, so potassium hydroxide plus our compound hydrogen peroxide. Then potassium ferricyanide directly converted into potassium ferrocyanide. Potassium ferrocyanide, formula K4FeCN6. K4FeCN6. K3FeCN6 converted into K4FeCN6. And compound name is potassium. Potassium ferrocyanide. Potassium ferrocyanide. Potassium ferricyanide converted into potassium ferrocyanide. Formula K4FeCN6. And byproducts are very simple. Water molecule, water formula H2O and oxygen gas O2, H2O plus O2. Previous JEE mains question is potassium ferricyanide formula K3FeCN6. So potassium ferricyanide K3FeCN6 ferricyanide plus basic medium or alkaline medium potassium hydroxide plus hydrogen peroxide. Then potassium ferricyanide converted into potassium ferrocyanide ferrocyanide, and byproducts are water and oxygen. So very simple, 2 into 3, 6 plus 2, 8 moles of potassium. So 2 into 4, 8 moles of potassium. Next 2 hydrogen plus 2, 4 hydrogen atoms, 2 into 2, 4 hydrogen atoms. And oxygen, 2 oxygen plus 2, 4 oxygen atoms, 2 oxygen plus 2, 4 oxygen atoms. So this is reducing property of hydrogen peroxide. Generally oxidation means increasing of oxidation state and reduction means decreasing of oxidation state. For example, very simple. Generally potassium ferricyanide formula K3FeCN6. So this is potassium ferricyanide. And potassium ferricyanide converted into potassium ferrocyanide K4FeCN6. Potassium ferricyanide converted into ferrocyanide. So central atom is iron. So X 6 moles of cyanide. So 6 into -1. Cyanide is a negative ligand. And 3 moles of potassium, so 3 into plus 1. 3 into plus 1 is equal 0. Then x minus 6 plus 3 is equal 0. Then x is equal plus 3. So in potassium ferricyanide, iron has a plus 3 oxidation state. And next one, potassium ferrocyanide. Formula K4FeCN6. Same central atom is iron. So X 6 moles of cyanide, 6 into -1. 4 moles of potassium, 4 into plus 1 is equal 0. So very simple, x minus 6 plus 4 is equal 0. Then x minus 2 is equal 0. Then x is equal plus 2. So iron has a plus 2 oxidation state. So plus 3 converted into plus 2. So decreasing of oxidation state. So decreasing of oxidation state means reducing property. So okay. So reaction with potassium ferricyanide formula K3FeCN6. Okay. And alkaline medium potassium hydroxide plus H2O2. Then potassium ferricyanide converted into potassium ferrocyanide K4FeCN6. And byproducts are water and oxygen. So ferri high oxidation state. Ferro low oxidation state. So ferro low oxidation state, ferri high oxidation state. So these are reducing properties of hydrogen peroxide. So first reducing property, reaction with chlorine. Second one, bromine molecule formula Br2. Third one, ozone formula O3. Next disilver oxide formula Ag2O. Sodium hypochlorite formula NaOCl. Lead dioxide formula PbO2. And acidified potassium permanganate KMnO4. Next presence of alkaline medium. So react with potassium ferricyanide formula K3FeCN6. So these are reducing properties of hydrogen peroxide. Okay. So properties of hydrogen peroxide topic is completed. So first of all, hydrogen peroxide formula H2O2. Preparation methods of hydrogen peroxide. And Roman number 1 laboratory methods like sodium peroxide plus H2SO4, barium peroxide plus H2SO4, barium peroxide plus water plus carbon dioxide. Next industrial methods, so bulk preparation methods, that is electrolytic method. And second one, very important method, auto oxidation. Next properties of hydrogen peroxide, oxidizing properties of hydrogen peroxide. Next reducing properties of hydrogen peroxide. So potassium ferri means high oxidation state, so plus 3. Ferro means low oxidation state. So ferricyanide converted into ferrocyanide. So plus 3 converted into plus 2. So decreasing of oxidation state. So one of the reducing properties. So these are properties of hydrogen peroxide. And most important topic is needed. Okay, next one. Next, last and final topic in hydrogen and its compounds. So last and final topic, an important topic. So hydrides, very important topic. Hydrides. So what is meant by hydrides? What is meant by hydrides? Very simple. Hydrogen combines with almost all elements. Hydrogen combines with almost all elements except zero group elements. Except zero group elements or AJ group elements. Except zero group elements or AJ group elements. So and to form hydrides. So hydrogen combines with almost all elements. So hydrogen combines with almost all elements except zero group elements. That means helium, neon, argon, krypton, xenon, radon. Except zero group elements. So and to form hydrides. So finally, what is meant by hydrides? Very simple definition. Hydrogen combines with almost all elements except zero group elements. That is helium, neon, argon, krypton, xenon, and radon. And to form hydrides. Except zero group elements. That means hydrogen does not react with zero group elements. So finally, hydrides means hydrogen combines with almost all elements except zero group elements and to form hydrides. And further, hydrides are classified into three types. So first one is hydrides are classified into three types, and first one is very important. Ionic hydrides or saline hydrides or salt-like hydrides. Saline hydrides or salt-like hydrides. So first one is ionic hydrides or saline hydrides or salt-like hydrides. And second one is covalent hydrides. Covalent hydrides or molecular hydrides. And third one is very important, metallic hydrides. Third one is metallic hydrides or interstitial hydrides. Or non-stoichiometric hydrides. It is also called non-stoichiometric hydrides. So hydrides are classified into three types. So first one is ionic hydrides or saline hydrides or salt-like hydrides. Second one is covalent hydrides or molecular hydrides. And third one is metallic hydrides or interstitial hydrides or non-stoichiometric hydrides. So hydrides means hydrogen combines with almost all elements except zero group elements and to form hydrides. And hydrides are classified into three types: ionic hydrides, covalent hydrides, metallic hydrides. So first one subheading, that is ionic hydrides or saline hydrides or salt-like hydrides. So first one is ionic hydrides or saline hydrides or salt-like hydrides. So most of the S block elements. So the S block elements the S block elements, the S block elements, S block elements, that is first and second group elements are alkaline and alkaline earth metals. So the S block elements are first A, second A group elements are alkaline and alkaline earth metals, are form ionic hydrides, ionic hydrides or salt-like hydrides, or saline hydrides. So the S block elements are form ionic hydrides. So the significant covalent character, is found in lithium hydride LiH, beryllium hydride BeH2, and magnesium hydride formula MgH2, capital M, MgH2. So lithium hydride, beryllium hydride, and magnesium hydride. Actually, ionic hydrides, the S block elements are formed ionic hydrides. S block means first A and second A group elements. Generally, first A group elements are lithium, sodium, potassium, rubidium, cesium, and francium. Francium is a radioactive element. Second A group elements: beryllium, magnesium, calcium, strontium, barium, and radium. Radium is a radioactive element. So cesium next to francium is a radioactive element. Okay. So the S block elements are formed ionic hydrides. The significant covalent character, very important point. The significant covalent character is found in lithium hydride, beryllium hydride, and magnesium hydride. And most important point, beryllium hydride formula BeH2 and magnesium hydride formula MgH2. Beryllium hydride and magnesium hydride both are polymeric in structure. Very important point. So beryllium hydride and magnesium hydride are polymeric in structure. Poly means many, whose, long, length. Okay. So beryllium hydride and magnesium hydride are polymeric in structure. Okay. So first of all, the S block elements are formed ionic hydrides, or saline hydrides, or salt-like hydrides. The significant covalent character is found in lithium hydride, beryllium hydride, and magnesium hydride. Next, beryllium hydride and magnesium hydride are polymeric in structure. And next, most important point, ionic hydrides dissolved in water. And to form basic solution and hydrogen gas. For example, sodium hydride formula NaH, one of the ionic hydride. Plus dissolved in water molecule H2O. So very simple answer, NaOH, sodium hydroxide, one of the base plus hydrogen gas formula H2. So base ionic hydrides like sodium hydride dissolved in water and to form basic solution like sodium hydroxide solution and hydrogen gas. So this is ionic hydrides, saline hydrides, or salt-like hydrides. So finally, ionic hydrides means the S block elements are formed ionic hydrides. S block elements, first A and second A group elements, are alkaline metals and alkaline earth metals. Alkaline metals: lithium, sodium, potassium, rubidium, cesium, francium, Fr. And second A group elements: beryllium, magnesium, calcium, strontium, barium, and radium. And next, the significant covalent character. The significant covalent character is found in lithium hydride, beryllium hydride, and magnesium hydride. And next one, beryllium hydride and magnesium hydride are polymeric in structure. Polymer, many use or number of molecules. And next one is sodium hydride are ionic hydrides dissolved in water and to form basic solution and hydrogen gas. So this is ionic hydrides or saline hydrides or salt-like hydrides. And second one, so hydrides are classified into three types. So first one is ionic hydrides, or saline hydrides, or salt-like hydrides. Completed. Next one. Second one. So first one ionic hydrides, salt-like hydrides, or saline hydrides, and second one covalent hydrides. hydrides or molecular hydrides or molecular covalent hydrides or molecular hydrides. So first one ionic hydrides or solid-like hydrides or saline hydrides, and second one covalent hydrides or molecular hydrides. So most of the P block elements are formed covalent hydrides. So most of the P block elements are formed covalent hydrides. That means third A group, next fourth A group, fifth A group, sixth A group, and seventh A group elements. Are formed covalent hydrides or molecular hydrides. Third A group elements, fourth A group elements, fifth A group elements, sixth A group elements, and seventh A group elements. Most of the P block elements are formed covalent hydrides. That means third A to seventh A group elements. And further covalent hydrides are classified into three types. So first one is very very important. Electron deficient hydrides. Electron deficient hydrides. First one is electron deficient hydrides. So second one, electron precise hydrides. Second one is electron precise hydrides. And third one is electron rich hydrides. Okay, so these are covalent hydrides. So generally covalent hydrides means most of the P block elements are formed covalent hydrides. That means third A to seventh A group elements. And covalent hydrides further classified into three types: electron deficient. Second one, electron precise, required number of electrons. Third one, electron rich, excess number of electrons. So electron deficient hydrides, electron precise hydrides, and electron rich hydrides. So these three are covalent hydrides or molecular hydrides. Okay. And first one is electron deficient hydrides. What is meant by electron deficient hydrides? So very simple, electron deficient hydrides. An electron deficient hydrides as a less number of electrons. And electron deficient hydrides as a less number of electrons. To write the Lewis structure. So an electron deficient hydrides as a less number of electrons to write the Lewis structure. For example, most of the third A group elements are formed electron deficient hydrides. And best example of electron deficient hydride, that is diborane. Generally diborane formula B2H6. Diborane formula B2H6. So finally, electron deficient hydrides means an electron deficient hydrides as a less number of electrons to write the Lewis structure. So most of the third A group elements like boron, aluminum, gallium, indium, thorium, these are third A group elements. So most of the third A group elements are formed electron deficient hydrides. Example, diborane formula B2H6. And these hydrides are electron deficient hydrides are act as a lone pair acceptors. That means Lewis acid. So these are electron deficient hydrides act as a Lewis acids due to lone pair acceptors. So in diborane central atom is boron, and boron has a MTR vacant orbital. So boron is a lone pair acceptor. So generally Lewis acid means lone pair acceptor and Lewis base means lone pair donor. So these hydrides are electron deficient hydrides act as a Lewis acids due to lone pair acceptors or presence of vacant or empty orbital. So finally these hydrides are act as a Lewis acids. Lewis acids. So this is electron deficient hydrides. And next one, electron precise hydrides. So electron deficient hydrides are act as a Lewis acids. Lewis acids. Next one. Second one, electron precise hydrides. Electron precise hydrides. Very simple. An electron precise hydrides. An electron precise hydrides as a required number of electrons. As a required number of electrons. Required number of electrons to write the Lewis structure. To write the Lewis structure. Electron deficient, less number of electrons. So electron precise, required number of electrons. So an electron precise hydrides as a required number of electrons to write the Lewis structure. So most of the fourth A group elements are form electron precise hydrides. For example, best example of electron precise hydrides, that is methane formula CH4. So generally methane structure tetrahedral structure. CH4 tetrahedral shape. So this is electron precise hydrides. So electron precise hydrides as a required number of electrons to write the Lewis structure. So most of the fourth A group elements like carbon, silicon, germanium, tin and lead, most of the fourth A group elements are form electron precise hydrides. Best example methane formula CH4. And structure of electron precise hydrides is tetrahedral shape. And last and final, electron rich hydrides. So first one electron deficient, second one electron precise, and third one electron rich hydrides. And third one is electron rich hydrides. Electron rich hydrides. Okay? Electron deficient, electron precise, electron rich hydrides. So an electron rich hydrides has a excess number of electrons. An electron rich hydrides has a excess number of electrons. And these excess electrons are act as a lone pair of electrons. So these excess number of electrons are act as a lone pair of electrons. So these excess electrons are act as a lone phase. So most of the fifth A group elements, sixth A group elements, and seventh A group elements are form electron rich hydrides. So finally electron rich hydrides means, so an electron rich hydrides has an excess number of electrons, and these excess number of electrons are act as a lone pairs. Most of the fifth A group elements, sixth A group elements, and the seventh A group elements are form electron rich hydrides. For example, fifth A group elements are nitrogen, phosphorus, arsenic, antimony, bismuth, and best example of electron rich hydride in fifth A group elements, that is ammonia formula NH3. In ammonia, nitrogen has a one lone pair, excess electrons, and these excess electrons are act as a lone pair of electrons. Lone pairs. Next, sixth A group elements, water, best example water. Actually, sixth A group elements, oxygen, sulfur, selenium, tellurium and polonium. And sixth A group element hydride is water formula H2O. So in water center atom is oxygen, and oxygen has a two lone pairs. Next is seventh A group elements, for example chlorine, bromine, iodine. So seventh A group elements, best example hydrochloric acid. In hydrochloric acid, chlorine has a three lone pairs, excess electrons. So these are best example of electron-rich hydrates. Electron-deficient hydrates, best example dichlorine formula B2S. Electron-precise hydrates, best example methane formula CH4. And electron-rich hydrates, best example ammonia, 5th A group element ammonia, 6th A group element water, 7th A group element hydrochloric acid. And these excess electrons are acting as a lone pair of electrons. For example, in ammonia, central atom is nitrogen. So nitrogen has a one lone pair. Then in water molecule, central atom is oxygen, and oxygen has a two lone pair of electrons. Next, in hydrochloric acid, central atom is fluorine, and fluorine has a three lone pair of electrons. So, and all electron-rich hydrates are act as a Lewis bases. Lewis bases. So, what is meant by Lewis base? Lone pair donor. Lewis acid means lone pair acceptor, and Lewis base means lone pair donors. So, in ammonia, central atom is nitrogen, and nitrogen has a one lone pair. So, this is lone pair donor. So, Lewis base. So, in water molecule, central atom is oxygen, and oxygen has a two lone pair. So, this is also lone pair donor. So this is Lewis base. So in hydrochloric acid, central atom is chlorine, and chlorine has a three lone pair. So this is also lone pair donor. So Lewis base. So Lewis acid lone pair acceptor, and Lewis base lone pair donors. Lone pair donor. So these are electron-rich hydrates, and best example of electron-rich hydrates: ammonia, water, hydrochloric acid. Okay. So generally hydrates are classified into three types. First one is ionic hydrates, saline hydrates are salt-like hydrates, and second one covalent hydrates are molecular hydrates, completed. And last one, final, third one. Third one, ionic hydrates, first one. Molecular hydrates are covalent hydrates, second one. And third one is very simple, metallic hydrates. Metallic hydrates or interstitial hydrates or non-stoichiometric hydrates. Non-stoichiometric hydrates. Okay? Metallic hydrates or interstitial hydrates or non-stoichiometric hydrates. Metallic hydrates or interstitial hydrates or non-stoichiometric hydrates. So many D block and F block elements. That means transition and inner transition metals. 3D, 4D, 5D, 6D, 4F and 5. So many D and F block elements are formed metallic hydrates, or interstitial hydrates, or non-stoichiometric hydrates. So best example of metallic hydrates: lanthanum hydride, formula LaH 2.87, non-stoichiometric 2.87. Next, zirconium hydride, ZrH and ZrH 1.3 to 1.75. So best example of metallic hydrates are interstitial hydrates or non-stoichiometric hydrates: lanthanum hydride LaH 2.87, zirconium hydride ZrH 1.3 to 1.75, non-stoichiometric ratio. So many D block and F block elements are formed metallic hydrates or interstitial hydrates or non-stoichiometric hydrates. Example: lanthanum hydride LaH 2.87, zirconium hydride ZrH 1.3 to 1.75. So see hydrates concept. Okay. So first of all, what is meant by hydrates? So hydrogen combines with almost all elements except the zero group elements and to form hydrates. And hydrates are classified into three types: ionic hydrates, saline hydrates, or salt-like hydrates. Second one, covalent or molecular hydrates, and third one is metallic hydrates or interstitial hydrates, non-stoichiometric hydrates. Okay. So next, best example of ionic hydrates: S block elements. Next, second one, most of the P block elements are formed covalent or molecular hydrates, and many D and F block elements are formed metallic hydrates. So see hydrates concept. Okay. So hydrogen and its compounds chapter is completed. So first of all, topics: dihydrogen, preparation methods of dihydrogen, properties of dihydrogen, uses of dihydrogen, and uses of dihydrogen as a fuel like water gas, carbureted water gas, coal gas, and semi water gas. And second topic, water formula H2O, and shape of the molecule and chemical properties of water. Next topic, hardness of water, temporary hardness of water, permanent hardness of water. So methods for removal of temporary hardness of water, methods for removal of permanent hardness of water. Next, heavy water. Heavy water formula D2O and chemical properties of heavy water. Chemical properties of heavy water. Next, hydrogen peroxide formula H2O2. Preparation and properties of hydrogen peroxide. Oxidizing properties of hydrogen peroxide. Reducing properties of hydrogen peroxide. Next, hydrates and classification of hydrates. Ionic hydrates, covalent or molecular hydrates, interstitial hydrates, metallic hydrates, or non-cytochromatic hydrates. So this is hydrogen and its compounds. So hydrogen and its compounds chapter is completed. Okay, thank you.